The result of this is the smaller bits in the image of noise are removed as well. So at this stage, what we're presented with is two images of silhouettes of the balls. The centroids of those ball locations are then calculated. So you have two images with two XY coordinates of the balls in those images. This is then used to reconstruct the 3D environment. So for reconstructing the 3D environment, I've used the Point Grey Research stereovision camera. This is a pre-calibrated camera where certain parameters are already defined within the unit itself. So for example, the baseline, the distance between the two cameras, and the focal length are already known. So this information is used along with the disparity to be able to reconstruct the environment. The disparity is the distance, the difference between the 2 points in the different images. So this is the main idea behind reconstructing the environment. The reason for using a pre-calibrated camera is because it greatly simplifies the process of doing this. Mainly because those parameters are already known, so we don't have to identify them. The one problem we had when doing this is that we were measuring incorrect measurements. So, for example, locating the ball 1 metre away from the camera and recording that measurement got a result of 1.5 metres or something similar. The results were quite a way off and were not accurate at all. We identified several areas for these reasons for this problem, one of which is the radial distortion. The radial distortion is the effect of the curvature of the lens on the image. So if you took a photo of a straight line, for example, the edge of the board here, in an image it would appear curved at the corners. So this is one source of error for this. Also the disparity as well. So where this relies on the actual locations of the balls in the two images, the left and right images, there is a certain amount of error occurring from the actual recognition of the ball as well. Then there's also the element of the calibration of the unit as well. So factory calibrated units, there's a certain amount of error present in that calibration as well. So these were some of the sources of error that we encountered. Now I'm going to talk to you about how we overcame this problem. We performed system identification on the unit. So we conducted an experiment whereby the measurements between the camera and the ball were measured. So, for example, here the camera is located at a distance from the ball. 30 readings are recording the disparity. This is then moved back at different increments and recorded again. So I've recorded the disparity at different distances from the ball. With this data, I've then been able to plot the data and produce a curve which fits that data. We've been able to identify the relationship between the disparity. So the reason for doing this is to improve the accuracy of the system, and this is then used while reconstructing the 3D environment. So next I'll actually show you the data that we collected. Along the bottom here we can see the disparity, which is measured in pixels. And across here we can see the coefficient that we've used for scaling the disparity. And then the red line here, the red dots, or rather, sorry, the blue dots of the system, which we've recorded, and then we've fitted that system with a curve, which is represented here by the red line. So this is how we've overcome the problem of the inaccuracy of the measurements. So that was the vision process, which recognises the ball and identifies the location of the ball. The next process is the pan-tilt unit process. The pan-tilt unit is this device here. This connects via a serial interface to the robot, and the idea behind this process is that it's going to track the ball to maintain the position of the ball in the centre of the image. So it's similar to tennis umpire watching a game. His head tracks the ball from side to side across the court. This is what the pan tilt unit allows the camera to do. It moves the position of the camera. To do this, I've written a proportional controller, which basically defines the set point to which to move the camera to. So this is how the ball position is maintained. Then the third process is the fuzzy logic controllers process. Here, this process controls the movement of the vehicle. I've split the control into two controllers. The first one is the lateral control. The inputs to this are the direction of the lead vehicle, so whereabouts it is in the environment, and also the speed of the following robot, so how fast it's currently travelling at the moment. The output of this controller is a change in heading, the delta heading. For this, I've used 25 rules. So this controls the heading of the robot. The second controller controls longitudinal control, so how fast the robot's travelling. So this is the adaptive cruise control module. The inputs to this are the distance to the leading vehicle, which comes from the stereovision unit, and the speed of the vehicle, so how fast it's travelling. And the output is a change in speed, so it changes the speed according to its information. And again, it has 25 rules. So these two controllers are separated to isolate the cruise control unit, the change of the speed from the other controller. So that's what we're focusing on here. So these controllers are in one process. They've been designed based on the Mamdani fuzzy inference model. This is a model which has fuzzy sets which represent the inputs and outputs. So we use linguistic terms to describe how the system is and how we want to change the system. The method for designing this has been from operator experience. The operator I've defined to be myself. I've experience of driving vehicles and guiding the robot, teleoperating it myself. Creating membership functions according to my knowledge of this experience. And also the control rules as well, so it's been the same method for this. One important operator I've used is the implication operator. For this I've used Larson's product. This has been defined by Joe Mendel to be good for control engineering problems. It's commonly used for this application as well. Then the final stage of the controller is the defuzzification. For this I've used the centre of area. So it's the same as before with the centroid method within the image processing algorithm. So this is how the controller has been designed. So that presented the design of the system. Now I'm going to talk about the experiment of the system. So the general outline here, the idea behind this is here. You can see the following robot. So this is autonomous. This is what's sensing the leading robot, just here. You can see the stereovision camera on top, little gold block there, that sits on top of the pan tilt unit. So this senses the leading vehicle and changes its speed and direction accordingly. So the way to measure the distance here between the two vehicles to identify how accurate our system is to use a laser rangefinder, this blue block here, on top of the leading robot. This faces backwards, reading the distance between the two robots. We're aiming to maintain a distance of 1 metre, so that's our set point between the two robots. And so the laser here provides measurements here of how closely we're doing this. It records these readings and then I'll pass them offline. So the readings it records 180-degree field of view of what it sees in front of it. I've taken the closest image, the closest reading, which I've assumed to be the following robot. From this, I've then produced a single measurement for a single run, which is the root mean square error. This provides a measure of how well the system is